all it is. All right, so let's start out with some of the material that we have on Blackboard. We're going to kind of pick up from where we left off last week. Remember, we're playing around with our software. We're working with Excel. We're working with SPSS. Tonight, I'm going to post some links to some YouTube videos that are pretty good, that are an introduction to R and to an introduction to R Studio, which is a graphic user interface that you can use with R to make it a little bit simpler to use. I'm not going to get into R tonight because I'm not a glutton for punishment, unlike most statisticians. But if you are a glutton for punishment, or a nerd, or somebody that really likes hacking into stuff and stuff like that, it is a lot of fun to play with. So you might want to consider at least taking a look at the videos that I give you the links to. They're only about 10 or 15 minutes long, and they'll at least give you an introduction to it. Okay, but for the most part tonight, we're going to work with Excel and SPSS, which is a little bit friendlier for most of it. Okay, so if you downloaded the files that we had there, I'm going to start with this file called Descriptive Statistics Exercise number 1. It's an Excel file, and I'm going to open that up. Okay, the reason why I'm doing this is because I have a long-standing belief that no matter what happens, that you should understand what the hell a standard deviation is before you get out of this class. And as much as I trust you when you tell me, I know what it is. At no other point in this class you're going to actually calculate it from raw. So we're going to actually do this. You can follow this along watching me, or you can actually do it yourself. Wouldn't hurt to do it yourself because you might learn, get a little bit of practice with Excel if you're not really used to using it. In fact, there's one little particular trick here that many casual users of Excel probably would benefit learning from. It's one little, even that one little trick is really going to save you a lot of time in the future. Okay, so first of all, I'm going to calculate a bunch of descriptive statistics for numerical variables. Now, usually when we're dealing with categorical or nominal variables, we're looking at frequency. When we're looking at numerical variables, we have the opportunity to organize them in a way that helps us understand better how those numbers are distributed, how blood pressures tend to range. In other words, if we took a look at the data for the population in the United States for blood pressure, and we saw the descriptive statistics like the mean and the variable and the statistics that show us the variables such as standard deviation, we could look at someone's blood pressure and say, geez, he's got a blood pressure of 89. I kind of know where he stands in terms of the rest of the population. Where if we just look at a page full of numbers or 1,000 blood pressures or something like that, it's kind of hard for us to interpret all those numbers, given our meager human brains and stuff like that. So it's interesting. There are certain mathematical processes we can use to summarize data, and we're going to try one right now. Okay, first thing I'm going to do is I'm going to take the average. The average is just the arithmetic mean, and or the mean rather. It's just the arithmetic average. You can use either way. So in Excel, we know we have built-in functions that we can use. So I'm going to do it a couple of ways. I'm going to say this is the sum of all of these 20 numbers. This is just a distribution that I created. Oh, there's 19 numbers. And I'm going to close parentheses, just a sum. And you know what I'm going to do? I'm going to add another. There's 18 numbers. Oh, you're right. There's 18 numbers. I have a header there too. Okay, just as well. Okay, somewhere or other when I reformatted it, I must have lost a couple of numbers there. Okay, so I'm going to take the sum of all of those 18 numbers and divide by 18, the count for all of those numbers. There actually is a function in Excel called count. So I could actually put, instead of 18, I just say count, parentheses, and highlight those numbers again. So it fills in that A2 through A8, A19, 20. I was going to do the same thing. It's just adding them together and dividing by 18. And it comes out to 99.94. Okay, pretty convenient, right? Pretty much 100 is the mean for this distribution. The count, if you want to see it separately, just so you know it really works, parentheses, and I'm going to highlight all these, and I'm going to hit enter. The count is 18, 18 values there. Okay? I just took advantage of two functions in Excel, and again, the way I got to those functions is I said equals. I'll just do that over here so you can see it. Equals, I trust this is displaying, right? me if it's got to be plain. Equals and count. I just typed in the variable name. Look, as I did it, SPSS narrowed the range down as I'm typing for available available functions that it understands. When I put the parentheses in, it realizes, that's what I want is I want the count. And it gives me a hint. Well, tell me where the values are. Value 1, value 2, et cetera, dot, 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 dot. And you can just tell it, type in A2 through A18, A19, or you can click down on A2. It'll fill the number for you. I'm not lifting up yet. And drag until you get to A19 so it knows to count that range of cells. If I had typed it in, I would have typed in A2 colon A19 to let it know that those are the numbers I wanted to find the count for. Okay, so I'm going to continue to do that now. Now, I'm going to say to myself, well, what is the average here? Well, the average is 99. How can I define how variable these numbers, how far these numbers are from average? For instance, I could have 18 numbers where all of the numbers are between 99 and 101. There's very little variability. I could have an average of 100, but the numbers range from 20 to 180, a lot of variability. So I want a way of defining what the variability is. So I'm thinking a good way to define what the variability is to add up the differences between the mean and each individual value. So if I have something that has a lot of variability, there's a big difference between the mean and each individual value. When I add up all the differences between the mean and the values, then it's going to be a big number. If all the values are close to the mean, then the difference between the mean and each individual value all added together, it's going to be a small number. So that would kind of indicate to me what that is. So I'm going to calculate x minus x bar. Very frequently in statistics, we refer to the mean of a sample distribution as x with a bar over the top of it. Just quickly, the reason why we use that x with a bar over the top of it, to distinguish between the mean of a sample and the mean of a population. When we start talking about these statistics applied to an entire population, we use Greek letters. Mean is going to be described as mu, the Greek letter mu, the little u. Okay, mean was a sample is going to be x bar. It's going to be a letter with just a bar over the top of it. Standard deviation for a population is going to be sigma. Let's say sigma. If you don't know what it is now, you'll know what it is in very short. For a sample, we just call it SD, short for standard deviation. Okay, with regular letters. Okay, so the first thing I want to do is I want to subtract each one of these values from x bar. So I'm going to skip this column over here, and I'm just going to do it right in there. I'm going to say, okay, this cell here is going to be equal to the value x minus the value of x bar, which is 99.94, and that's about -1, roughly -1. Okay, so now that's how we can define how many decimal places are displayed throughout this. I'll show you how to do that later on. We're not worried about that right now. Now, the next thing we can do with Excel is we can, as we looked at last week, we can take a formula and we can copy that formula so that we don't have to repeat it for each row where we want to repeat the same calculation. So we want to repeat the same calculation here in this cell for the next cell and the next cell and the next cell. In other words, 93 minus x bar, 109 minus x bar, and so on and so forth. Okay, so I'm going to click on that. I'm going to drag down. And depending on where you're using a PC or a Mac, you're going to see that there's a little symbol for fill on your home. So they use ribbons. Microsoft uses these ribbons instead of drop menus now. Got away from drop menus a few years ago. So it uses these ribbons. You'll find different functions in different ribbons. If we're going to draw a chart, you got to go over to the chart ribbon. But in a home ribbon, you're going to find most of the basic ones that you're going to use with Excel. Okay, so now I've highlighted this, and it says A2 through B21, right? And I want to copy that formula all the way down. So I click into the fill box and say fill down. Okay, and it's going to copy that formula all the way down. Okay, and let's see what I got. I got 86, I got this, I got, let's see, 104 minus 99. That's not 86, is it? That doesn't sound right, right? And something went wrong here, right? Let's click into this bar here. Unfortunately, what Excel does is that when it's doing the calculation between columns, it advances one row down for each column, right? So if you look at this formula, the first bar, A2 minus, A2 minus, how did I do that? What did I do there? Excuse me, B21, that's right, right? Now, if I go into, I'm going to hit escape. If I go into the next column, it says A3 minus B22. Well, the A3 part is right, but look what it's done. It's gone down to the next box, so it's subtracting 18 instead of the average. So what we want to happen here is we want only the A column to advance one at a time, but we don't want the mean, that minus part, to change. So I'm going to click into this first box, and I'm going to change that B21. I'm going to put a dollar sign in front of the B. I'm going to put a dollar sign in front of the 21. Okay? What I just told it is I want that B21 to be an absolute address. I don't want it to change. I'm going to hit enter just so it takes it. So from now on, when I click in there and drag down, and I say fill down, it's going to advance the first part, first cell, but it's going to keep the second cell the same. That difference is the difference between relative and absolute addressing. See, now it did it correctly this time. Okay, so we're going to add up all of the differences here. So equals the sum of all of these differences. We're going to add up all the sum of those, all of those differences. What's going to happen when I add up the sum of all the differences? Anybody want to make a prediction? It's going to add up to 0, right? It's pretty much, that's pretty as close to 0 as you can possibly get, 10 to the minus 14. It's going to add up to 0 because half of these numbers are above the mean, half of the numbers are proportionally below the mean, so that's not going to work for us. One of the ways we need to get rid of the negative, or we need to get this to have all positive signs. We can take the absolute value. Another way in mathematics of getting rid of negative signs is to square a number. Because if we square the number, negative number becomes negative number, it's a positive number, as is positive positive. So what we're going to do is we're going to take the difference between the mean and the the mean and the value, and we're going to square it this time. So we're going to say this column is going to be equal to this value times itself. I'm just going to repeat it twice. C2 times C2. I don't need to use absolute addressing because we want it to advance for both of these values going straight down. So we click in there, drag down, and say fill down. Fill, edit, fill. Where am I? I'm forgetting where I am. Fill down. Okay, so it's squared each one of those numbers. Then I'm going to go down here at the bottom. I'm going to add all those numbers together. Sum, parentheses, I'm going to add all of those numbers together. Okay, the sum is 892. Had these numbers been less variable, closer to 100, that number would be a smaller number now because the differences would all be smaller, the squares would all be smaller, and the sum that I collected at the bottom for all of these differences would be smaller. So that number depends on how variable each number is from the mean. Okay, so now that number is something called the sum of the squares of the differences. I'm making that red because that's your first important statistic that involves variability. It's going to come up very frequently in the future. Okay. Now, the next thing I'm going to do is I'm going to say, well, that number represents the variability for the entire group of numbers that I'm looking at, the entire sample. So now I want to define it. I just want to look at it as per variable, roughly. So one of the ways I could do that is I could say, okay, let's take the sum and divide by the number of variables, the count. We're going to take a little bit of a variation from that. And we're going to divide by not n, not the total number of variables, 18, but by n minus 1, 17. So I'm going to call that 17. As we move forward, we're going to discover that a lot of times when we look at the variation, we're going to start looking, we're going to be concerned, rather than the absolute count, by something called degrees of freedom. Okay? If you have one number, how many degrees of freedom do you have for that one number? You don't have any. It's that number. That's it. You have two numbers. How many degrees of freedom do you have? You have one, because you have one or the other. Three, you have 2 degrees of freedom, and so on and so forth. So we're going to be concerned about degrees of freedom going forward. This kind of ties into this thing. And for a lot of other reasons, it just works. It happens that it works better this way anyway. So I'm going to divide by 17 instead of 18. That's going to give a kind of an average of all the squares of the differences between the mean and these values. And that happens to be 52.52. I'm going to click on that. That number is called the variance. That's another number that you're going to be concerned about. A lot of times it's defined as S squared for a sample, or sigma squared for a population. Okay, that's the variance, call it S. Okay, so now that number is inflated. It's inflated because we created it by squaring all the differences. So now let's bring that number back into the order of magnitude that the original numbers were in by taking the square root of it. So I'm going to click in here, and I'm going to find the square root of the variance. Now, there is a function in Excel called square root, SQRT, parentheses. If I click on the 52, the box with the 52 actually, close parentheses, hit enter, it takes the square root of that 52. That square root now is our standard deviation. That's what we call SD or S very frequently. S squared is the variance, S is the standard deviation, and sometimes you see SS for the sum of the differences of the squares. Okay, so now those are important variables. I'm going to highlight that one, especially that one, that's particularly important. And I'm going to illustrate for you in a moment why that particular number is important. I heard Levy talking about the empirical formula, and we're a little bit ahead of the game in talking about the empirical formula, but I think maybe we can talk about it. But I'll get to that in just one more second when I finish this spreadsheet here. Okay, now the other thing that we're interested in, another way of describing this spread is to describe the minimum and the maximum for the population, for the sample rather. So the minimum is equal to minimum, MIN, parentheses, that's the minimum, and I just highlight the original numbers, what I want to highlight. Okay, and minimum's 88. If you had sorted it, you would see that would be right. And the maximum is equal to MAX, surprisingly enough, parentheses. And find the maximum for all of those numbers. Okay, if you were uncomfortable with the clicking and dragging, you could just type in the range of numbers. Okay, and the range is just the difference between those two. I'm going to start with the bigger number, the maximum, 114 minus 88. Okay, 26, range is 26. Simple enough. Relatively unsophisticated measurement, the range and the minimum and maximum. Literally just tell you how far apart the lowest number and the biggest number is. A little bit more descriptive are percentiles. Okay, so in other words, when you took the GREs or the SATs, they gave you a score and they told you, oh, your score was 700, and most of you guys got over that. 700, 800 or something like that on each test. So they gave you a score of 779, right? That doesn't mean anything in the real world to you because you don't know how anybody else did, but they also gave you a percentile. And they might have said, oh, you got 779. That means you're in the 3rd percentile. In other words, 3% of people scored above you, 97% of people scored below you. Okay, so percentile is a little bit more descriptive, gives a little better idea of where we are in terms of the distribution of all these numbers. Now, Excel has a way of calculating percentiles. 2 of the percentiles we're most interested in is the 25th percentile and the 75th percentile, because that's the middle 50% of all the people. Anybody outside of that is going to be above the top 25% or the bottom 25%, but the middle 25%, yes. I'm sorry, say again? No, they're not. It's a different number. We're going to take a look at it. In fact, I love the fact that you asked that because we're going to talk about the empirical formula, and that's going to describe to us what percentage of the values in the normal distribution are different from the mean by 1 standard deviation, by 2 standard. We're going to get. I'm glad you brought that up because that's an important distinction between percentiles and the standard deviation. So 75th percentile is a function called percentile. Percentile, parentheses, and it asks me for the array and k. The array is the list of numbers. Oops, I messed up there. No, just percentile parentheses is good enough. For our purposes, that's good enough. Percentile, just a word, parentheses. And I'm going to highlight that A2 through A19, comma, and that K is the percentile, as described as a fraction, 0.75. And I'm going to close parentheses, I'm going to hit enter. 104 is the 75th percentile. 75% of the values are above, 25% of the values are above 104, 75% are below 144. I'm going to do exactly the same thing for the 25th percentile. Remember, since this is recording, you'll be able to go back over this a little bit slower and scrub through it slower if you want to and see this. Equals percentile, parentheses. Again, the array is the list of numbers, comma, the percentile is, in this case, 0.25. And if you don't remember whether it's expressed as a decimal or a whole number or something like that, you can go into the help function, for the help for the function, various functions, and look up a description of how to use the function. I'll show you that in a second. Percentile, I'm going to hit enter, and that's the 25th percentile is 94. Okay. Now that means 50% of the values are between 94.5 and 104. Okay. Interesting that it gave me a fractional number. It actually kind of interpolated, or because there wasn't really, because it's 18 people, and there was 9, the top 9 and the bottom 9, and then the 4.5 middle between the 4th person and the 5th person. It kind of interpolated the value for me. Okay, because there wasn't an actual person that was a 25th out of 100 or something like that. But I won't worry about that too much. Okay, so now the IQR, anybody remember what that stands for? Right, the middle quartiles, the 2 middle quartiles. So the interquartile range is going to be equal to, just as we had the range before, going to equal to 104 minus 94.5. So 9.5 is the spread for middle 50% of the people. Okay. So that's some interesting. We discovered how to do these calculations. Chances are you're never going to do these calculations again after today in biostatistics. You're going to use software to do it. But I mean, at least you got an idea of where the standard deviation came from if you've never worked it out by hand before. Okay, so hopefully that's what we've done. I'm going to save this and I'll upload it so you can look at the formulas later on. Completed. Save. Okay, good. So now what I'm going to do is I'm going to take a moment here, and the mean here was 100, and the standard deviation was roughly 7. I'm going to do a little bit different. I'm going to call it roughly 7. So I'm going to go to my notebook. Let me see if I can get to it here. There we go. I'm going to go to my notebook, and hopefully it's working. What's that? Keep it down. Big game. Let's keep this loaded with the software for this. Let me get this out of the way. Okay. There's stuff on I got that control panel on my screen, which I need to be able to see the chat box and so on and so forth, and some other control stuff. Occasionally I got to move it out. If you see me doing weird stuff or avoiding something that you don't see, that's the reason. Okay, so ink. Okay. So now, one of the things you're going to notice about normal distributions, and I'm going to draw this as a histogram, is that most of the values tend to be towards the middle. The height of each one of these bars represents the frequency for that particular range of values. For instance, in our distribution, this might be the range 95 to 105. This might be the range of 105 to 115, and so on and so forth. One of the things that we're going to notice about normal distributions is that they have a characteristic shape and can be described mathematically. And that shape is roughly the shape of a bell curve. And you're going to see more of this bell curve than you could ever see done in your life by the end of this semester. The interesting thing about this is that in our distribution, right, here's that bell curve in our distribution. In our distribution, if the mean, I'm going to use population mean here. If the population mean is equal to 100, and the population standard deviation sigma is equal to 7. I could have also done it for the sample. I'm just kind of switching gears here a little bit and talk about population. The interesting thing about this is if this is a true standard normal distribution, well, the mean's 100. The mean is always where? It's in the middle, right? So here's the mean here, 100. Okay, where's the median if it's a normal distribution? It's the same thing, right? Unless if it's skewed, that's a different story. But the median, the middle value, and the mean are in exactly the same spot. What does that tell you about the shape of the area below and above the mean? They're symmetrical. They're exactly the same shape. Okay. Interesting thing about this standard deviation, I can predict that approximately 64% of the distribution is within one standard deviation below the mean and one standard deviation above the mean. I can also predict that 95% of the population, I'll put it up there so it can be read a little easier, is between two standard deviations below and above the population, the mean. I'm sorry, say again? That's a percentage. That's a percentage of the people. You can look at it as two, I think it was 64, 68. 64. That's called the empirical rule. We're going to learn about the mathematics. Right now, that's that you take that on faith kind of right now, okay, that's the way normal distributions work. When we talk about probability, you'll actually get into the point, especially in 751. 750, we really don't approach it that much. We don't get into it that much. In 751, you may get a little bit of the theory in terms of like the mathematics of this distribution and how it's tied into the probability of randomly selecting people and how half the time they're going to be below the mean, half the time they're going to be above the mean, and how frequently you'll find people a lot below the mean and above the mean, and so on and so forth. But this distribution, this normal distribution, that represents the way that numbers that are clustered around a mean distribute themselves naturally if they're if the difference between being higher and lower is just due to chance. I'm going to show you a little bit of a video at some point of a demo of a kind of almost like a pinball machine that's at the Queens Hall of Science, the New York Hall of Science in Queens. They'll kind of like illustrate this for you. Yes. 95% of the population is between two standard deviations below the mean and two standard deviations above the mean. And I can even go further and talk about three standard deviations above and below the mean. And that's represented by 99.7% of the population, if it's a true normal distribution, is between -3 standard deviations below the mean and +3 standard deviations above the mean. Okay, so for the sample that we were looking at right now, assuming it was population, for instance, okay, what percentage of the people would be, what value would represent the lowest and the highest value for 95% of the population, the middle 95% of the population? What would be two standard deviations below the mean and two above? So two standard deviations would be 14. So 14 less than from 100 is going to be 86. 14 added to 100 is 114. So for this distribution, we can say that 95% of the people in this population have, let's say it's a blood pressure between 86 and 114. Okay, only 5% of the population has a blood pressure that's not in this range. What percentage of the people do you think is below 86? Remember, it's symmetrical. 2.5%, right? Okay, we've got a bright group here, I can tell. And 2.5% would be above it. So why is that important to us? That's important to us because now we know if someone walks into our clinic, they have a blood pressure 85, that's unusual. If they're 3 standard deviations from the mean, which would be 21 from that, which would be 79, that's really unusual, right? That's less than 1/100th of 1% of the population has that blood pressure, or above 121. Okay. Do you need to understand this at this stage? No. I just thought it was a good idea to introduce you to this because it'll start to make sense to you how important that standard deviation calculation, that calculation we just went through for sum of squares and variance and standard deviation. Now that applies to all normal distributions. I'm going to draw another normal distribution very briefly here. Okay, here's another normal distribution. Okay, let me just do that. This normal distribution, oops, that's not a very pretty one. Okay, let me try that again. Oops, what's happening now? Undo. There's one undo. Okay, I'll do it over here. This normal distribution is very tall and narrow. Let's say the mean of this one is 100, and the mean is 100, and the standard deviation is equal to 2. Okay, 95% of the people in this population are between what two values? It's going to be 96 to 102, 104, right? Everybody agree with that? 2 standard deviations below, 2 standard deviations. So the only thing that changed here was the standard deviation. But now, since this property always holds up for normal distributions, I have a powerful tool here to understand just from 2 numbers to understand how the numbers, heights, blood pressures, blood sugars for this population is described. So just one more example, and this is going to be something that looks like this. This one, the mean is 100, and the standard deviation is equal, the sigma the standard deviation is equal to 35. Okay, what percentage of the population is let me put it this way. If someone walks in with a blood pressure of 35, 70, of 175, right? He's going to be in the top, what percentile? The top 2.5 percentile, because the range for 2 standard deviations, 95% of the population, is 100 minus 2 standard deviations which would be 30 or dead, and above. I'm making these numbers up, right? And 35 above 70 would be 170. You know this guy's all the way up here, right? Now, and we also know for 1 standard deviation, it would be between 100 minus 35 would be 65 and 135. We know a lot from just those 2 numbers, the mean and the standard deviation, assuming it, and we deal with a lot of normal distributions. That's why this stuff's important. Okay, let's move on from that. Okay, everybody okay with that? Right? Not complicated. That's called the empirical rule. It's a little bit ahead of the game. We're really going to get into that next week, and we'll get into even more complicated usages of it. I don't need this right now. Later. Okay, so let's take a look at the next version of this. The next version of this I'm going to look at is exercise 1 histogram. Descriptive Statistics. Exercise 1 histogram. Okay, so I got the same 18 numbers here. I want to, it's nice to describe this using the mean and the standard deviation. Problem with that is that's not a very visual measurement, is it? So very frequently we like to see histograms. A histogram is a nice graphic representation of what this information looks like. So the way we would create a histogram is that we're going to create bins. And these various bins are going to represent the frequency that we have a person in this population that has that value within that range. So I made up these bins myself. I know that the lowest value was about 89 or something like that. The highest value was about 114. There's a lot of ways that you could do these bins, right? I could click in here and I can say, let's see, for 85 to 89, I'm going to say I want the count of, and I can ask it to count all those numbers that are between. You can actually use little if statements in here. And you can say if the value of these numbers is between, say, 80 and 85, 80 and 89, 85 and 89, then count only those values that are between those two numbers. Okay. Usually the way you do that is you do a count for up to less than or equal to this, and then minus count that's below that, and you can do these various ranges. That's a little complicated, right? So for our purposes for right now, since you rarely use Excel to do this, you're going to be using SPSS or R to do this most of the time. I'm going to do this a simpler way. I'm going to take all of these numbers. I'm going to say, highlight them. I'm going to say copy. I'm going to click into this top second box here, and I'm going to tell it to paste the numbers in there. Edit, paste. You can also do paste from, there's a, let's see, I think you could do fill down, but there's also a paste command down here somewhere too. Now on your PCs, it's probably on the right-hand side. Wherever it is. Don't know where it is right now. You'll find it, I'm sure. Okay, so now this time, while they're highlighted, I'm going to go up to the date on my Mac. Oh, you might have it in here under your data file, under your data ribbon. You might have it in there on your PCs. I want to sort these, right? So you can click on sort, and you can click ascending or descending, right? I'll click ascending, and it'll sort the numbers for me. Now, notice it said, oh, you know, if I do this, the numbers now will not be paired with the numbers to the left of it. So in other words, if this was like a list of patient names and their blood pressures, then they'd be all screwed up because they wouldn't be with the right person's name anymore. So it's warning me about this and asking me, do I want to expand this to include the columns next to it? I don't want that. I just want to sort this one column. So I'm going to say just continue with the current selection. I'm going to say sort. So it just rearranges them from the lowest number to the highest number. So for our purposes for tonight, I'm just going to simply tell it, okay, let's see, how many of these numbers are between 88 and 89? 85 and 89, well, two of those numbers are. How many of these numbers are between 90 and 94? Well, it looks like three of them are. How many of these numbers are between 95 and 99? 1, 2, 3, 4. How many are between, the pretty elementary version of this, 100 and 104? 1, 2, 3, 4, 5. How many are between 105 and 109? 1, 2. How many between 110 and 114? Only one, and that's it, I think. Okay, so now I kind of got a view of how these are distributed into bins. 3 between 105 and what? Oh, okay, thank you. Okay. Who asked you? I'm sorry, I didn't mean that. I didn't really mean that. Okay, so at any rate, one of the things that we can do in Excel is we can very quickly put together. We probably won't be doing it much after tonight because we're going to use more powerful software to create graphs for us, and that will avoid us having to remember all of these functions. I'm just going to highlight the two columns, and I'm going to go over to chart, and we're going to do a histogram, right? A histogram usually is in the form of it can be in the form of a bar chart, but we usually do it as a column. Okay, so I'm going to click on column and just cluster column. I'm sorry? Oh, okay, yeah, on the PCs it's a little bit. For some reason, they've diverted. You know what it is also? I'm using a relatively older version on Mac also. But if you search around, you'll find these various functions. Okay, so there's our histogram, our representation of the distribution. It kind of looks like, remember, this is a small sample, right? And as a small sample, you can't expect it to be perfect. But what is this reminiscent of, what we're looking at here? It's reminiscent of that bell curve. It's reminiscent of a normal distribution. Had we had a big enough sample, indeed, it might have been much more like a normal distribution than this appears. Okay, so this gives you an idea of how the data is distributed, histograms. What's wrong with this histogram? What makes it different than a normal bar chart for, say, like a nominal variable like hair color, right? First bar would be hair color, second blonde, the second bar would be number of people, number of women that are redheads, and so on and so forth. What's the difference? Yes. Yeah, well, that's true because they're only within that bin. By looking at, you only look at it there. But yeah, it's ascends numerically, but also if you look here, there's space between them. Is there any space between these numbers? No, because you're either in one bar or the other bar. So a bar chart for a nominal variable has space between the bars. A column chart or a histogram chart doesn't have space between the values. So we got to adjust this. And there is, in fact, a way to do this. Let me see if I can't find it quickly. I just double clicked on one of the bars. And I believe if I get the right one, the options, see the over gap width here? I'm going to change that to 0. By all rights, that's the way a histogram should look, right? Because there's no gap between them. You're either in one bar or the other bar. It's continuous. With a nominal variable, then the gap doesn't mean anything. The gap doesn't disturb us because they're just different things. But this one, we want to show that it's continuous, that there's no gap between the values, right? So it's really kind of a true number line. Okay, so that's our histogram for this particular data, and it helps us understand this. One of the other kinds of charts that we're going to work with is called a box plot. You started to see that last week. That also informs us quite a bit about this distribution. And if you remember, you could actually kind of visualize here where our mean was, right? Our mean is somewhere in here, where our percentiles were, and so on and so forth, if you went back and looked at those numbers. Okay, so now let's see where we'll go from here. From here, we're going to start taking a look at this data in SPSS. So one of the ways that I want to deal with this in SPSS is I want to import this data into SPSS from my Excel file. So I'm going to double click on this, and there's my data. Now, this file that I call Descriptive Statistics, Exercise 1, Excel to SPSS, it's an Excel file, right? But the difference here is that I stripped of all the other stuff that's around. So it's only my raw data. In this particular case, I didn't even put a variable name in the top row, right? So this file is one that's going to be easy for me to import in SPSS. I'm going to close this file now. You got to close the file because SPSS is a wacky program, and one of the things it won't do is open a file that's already open in another program. For a $1,000 program, it does a lot. It's got a lot of like little glitches in it, but that's one of them. So I'm going to start SPSS. You should be able to find it. If you don't find it on your desktop there somewhere with a shortcut, you should be able to go into all programs. It'll be under IBM. IBM bought them up about 5 years ago or so. So it's most likely say IBM SPSS. So I'm going to start up SPSS. And I just got my license updated today. Remember last week I couldn't do this on this computer. I had to use the number one. Let me just make sure that recording's still on. Good. Okay. Okay, good. Okay, so it opens up with this. Usually I just leave this on here because I wanted you to see it. Usually I click off this box not to show it again, but it's kind of a setup box that comes up with where you can, from this box, tell it to open an existing file, tell it to open host files, and so on and so forth. Start a new data set, and so on and so forth. Usually I just cancel out of that, and I use the menus. Okay, so let's take a look at the menus. Go over here to File. I'm going to say Open. If I wanted to make a new data set, I would say New and Data, and I would get an open window like this with nothing in it. This looks like an Excel file, but it's not an Excel file. It's just a way to list. The rows represent subjects. The columns represent variables for that subject: age, name, date, weight, BMI, you name it. And I can actually start typing into this. I can't type formulas into this because it's not Excel. But it is kind of handy that it has that familiar looking interface at least. And it has a lot of drop menus that make doing the calculations easier. But rather than type in this data, I don't want to retype it because that's prone to error and not to mention being more work. I'm going to open a file and say Open. I'm going to ask it to open a data file. Okay, I'm going to navigate to where I happen to have my data file. Is on my desktop. Okay, and desktop. And it happens to be, I know it's in this folder, and I know it's in here. And I'm going to open my Excel. I don't see it. Reason why I don't see it is because right now it's only looking for SPSS data files, .sav. So I'm going to go down here to file types. I'm going to tell it to look for Excel file types. And now you can see all of the Excel files that were on Blackboard are now visible to me that weren't before. So I'm going to click on this one that says Excel, Descriptive Statistics, Exercise 1, Excel to SPSS, .xls, and I'm going to say Open. New box is going to come up, new dialog box is going to come up and says, aha, I see data in here between A1 and A18. Exactly what I expect, 18 numbers. Remember, I didn't put in this file, I didn't have the text on the top row. Now, you'll notice that there's a checkbox over here, bright blue right now. Read variable names from the first row of data. Do I have the variable name in the first row? No, I don't. So I want to uncheck that. If I don't uncheck that, it's going to think the first number is the variable name, right? And then only import 17 numbers. So I uncheck that. But if you do have a variable name in your Excel file, you did use the first row of data for your variable names in Excel, then you want to leave that check. I'm going to click OK. OK. And it pops open. And there we go. There's our data, right, imported into SPSS. Okay, now I can save this as I can say save as and save it as a .sav file and work with it in SPSS from now on. But before we do that, I'm going to do some actual calculations, including the ones that we just did now. I'm going to go over to Analyze because Analyze is going to be our basis for working with most of this information in SPSS. Okay, so I'm going to go to Analyze. I'm going to go to, well, Descriptive Statistics is what our syllabus says that we're discussing today. So I'm going to go to Descriptive Statistics. Well, frequencies. Frequencies is just going to count the number of times the value occurred. Is that appropriate for numerical variables? Not really. That's for nominal variables. Like frequencies, if we wanted to know how many are male and female, we would be interested in the frequency, number of male, number of females. For the descriptive statistics, numerical variables, we're interested in our descriptors, our mean, our standard deviation, and so on. So I'm going to click descriptives instead. Well, notice it named it V1 on its own because I didn't give it a variable name. We know that there's another version of this that shows as we discussed last week, the variable view, where I can give it a lot more information, including a new variable name and so on. I'm not going to bother right now. So it wants to know there's only one variable here, so this is simple. If there were many variables, this would give me the opportunity to select the variable I wanted to work with and move it into the box with that that SPSS is going to do the calculations for. Okay, I'm not going to bother with that. I'm going to click on options, and you'll see that there are a few selections there that you can make, but it's already checked off for mean and standard deviation. I'll tell you what, let's click variance also, since we've learned how to calculate that. And minimum, maximum, and I think that's probably range. Let's do range also. We know what that is. I'll click continue, and I'm going to click OK. Okay, SPSS now opens up a new window. Right, this new window is your output window. If you save your data window, that .sav file with your data, you're not saving this window. So you might want to remember to save this window separately, or you'll lose it. Okay, now just as a warning, don't send me your output files. It's a .spo file. Don't send me your output files because SPSS is very unfriendly to exchanging output files between versions, like version 19 to version 22, and so on and so forth. So what you'll send me instead is your data already formatted in some other form, like for instance in a Word document, something that you would communicate with the outside world. So what do we got here? We got our range was 26, our minimum was 88, maximum was 114, the mean was 99. Any of these numbers look familiar to you? It's exactly what we did going through all of those laborious calculations. That's why we're never going to do that again. Right? We understand how these numbers were generated now, but now we don't have to ever do that again. We can use SPSS or R or SAS or whatever program we feel most comfortable with to do these calculations. Okay, so there's our standard deviation, that very important number, standard deviation. We know a lot from knowing the mean and that standard deviation. We know a lot about this distribution if it's normally distributed now. Okay, so now that's very interesting. There also happens to be, if I click on Analyze, Descriptive Statistics, the third function down there is called Explore. It's the same as Descriptives, except it gives you more options. I'm going to go into Explore. Notice the box comes up, looks very similar. There's a couple of extra boxes there. The dependence list is going to be the variable that we're going to work with, right? Now, these other boxes, there's really nothing else left to put in there. But I do have some interesting buttons here that I didn't have before. Let's click on Statistics. Descriptive, 95. Let's leave that 95%. In about 3 weeks, we're going to talk about confidence intervals and stuff like that. And that's going to be important to us. Right now, let's leave that 95%. Percentiles. I'll check off percentiles. What the hell? Normally, I don't know what's going to happen with that. I think it's going to give me the main percentiles. I'm going to click on plots now. Well, look at this. Histogram is not checked. It's going to do a histogram for me if I ask it to. I'll check on histogram. Okay, and for now, I think that's all I'm going to check on the plots. Other options, well, it tells me, well, sometimes you have missing values. Person refused to give you their age, refused to give you all their other data, but refused to tell you if they were smokers or something like that. So Excel gives you a lot of ways to indicate why that data was missing, so you can make decisions as to like what you want to do with that data. For our purposes right now, there's no data missing anyway, so I'm not going to worry about that. In this bottom box here, it allows me to choose whether I want to display the statistics that I'm going to calculate only, or the plots only, the graphics, or both. I'm going to say both, and then I'm going to say OK. SPSS is going to recalculate all of those statistics we did before, except this time it's going to do the mean. It's going to do something called the confidence interval. It's going to do the median, the variable. We didn't get the median before. The variance, the standard deviation, minimum, maximum, the range, the interquartile range. Didn't do that for us before. It's also going to do something called skewness and kurtosis, which has to do with whether or not it's a perfect normal distribution or not, or how far from a perfect normal distribution. We're not worried about that right now. It gave me the percentiles. Look at that. It gave me the average, the 5th percentile, the 25th percentile, the 90th percentile. Here's the 25th and the 75th. That one's particularly important to us because that's the interquartile range. And it does something called Tukey's hinges. Now, if I remember correctly, I think Tukey's hinges is only the 25th and 75th percentile and the median. And I think that they're calculated without interpolation. In other words, it takes an actual value rather than interpolating between values. I think that's why they're whole numbers. I could be wrong. Don't quote me on that. You can Google it later on. But I think that's why those numbers are different than the other numbers. And it only cares about the interquartile. By the way, what's a Tukey? Is that like a bird? No, right. It's a statistician. I think it's pictures. It's on the banner. I'm not positive, though. There's a histogram. That's the same histogram we drew with Excel, right? Same shape. You can recognize it. And it also does something called the stem and leaf plot. In the old days, before we had graphics, one of the ways you display the distribution of numbers as a histogram is to display a range of numbers using the first digit. Like, for instance, what are the numbers that are between 85 and 89? Well, 8, 88, and 89. There are two numbers there. So you start with an 8 and put 8, 9, 8, put 8 and a 9 represent those two numbers. How about the numbers between 90 and 94? We'll put a 9 there and 93, a 93, and a 94. And if you look at this, when you do this for all the entire range of numbers, you can see that you got the same shape of your histogram. So back in the days when we only had text on computer displays instead of graphics, that's one of the ways you might display it. It's called stem and leaf, right? Kind of this is the stem, those are the leaves. Okay, and here's our box plot, our interesting way of displaying the same data. So it gives us the range, right? This lower leaf is the lowest number, which was 88. This upper leaf is the highest number, which was 114. And here is our 25th percentile, our 75th percentile, I think it was 104 or something like that. And our interquartile range is the difference between these two numbers. And that black bar in the middle is what? What's that? That's the median, not the mean, the median, right? Okay. And where should that be if it's a normal distribution? Right, middle of this gray box, and this gray box should be in the middle of this distribution. So this distribution happens to be skewed a little bit, right? And it's skewed to which side? It's skewed to the right because excuse me, the median. Let me think about this for a second. If the median down here, yeah, it's skewed. It's kind of hard to tell here, really, because this median is almost in the middle. It looks like it's skewed positively or to the right. Let's go back here. Actually, I think it's skewed to the left, right? So the median is to the left of the mean. The mean is to the right. So this is closer to this end than it is to that end. So the average is skewed positive. It's not easy to see on that one. Yeah. I think that I would say this is skewed. The tail is longer on this side. This is an easy one to see because kind of like the mean is buried in here somewhere. The average is buried in here. So really, the skew is which side is the average pulled? Is it pulled away from the mean that way? Or is the average pulled away from the mean that way? To the lower end or to the higher end? That's really what you're looking for. And you want to know something? Probably a better way for us to judge that. The median is 100. The mean is 99. So the average is being pulled down away from the median, right? So it's skewed to the left, right, or negatively. These two low numbers are skewing it to the left, okay? It would have been easier to see if they were like an odd value way to the left. This one's like they're really not. It's really a little bit harder to see that. Okay, so we just did in moments what we laboriously calculated before it got exactly